Hi Twin, back with another video of reviewing work. So let's just jump right into it, Twin. Okay, so I'm sure you know, but work is like in physics class known as force times distance. That's like you have to know that, right? But in calc, we're gonna be using this equation right here to represent that. Because let's say if f is constant, right? Is a constant. Then if we're looking at this, right, we could just take out the f. So that means work would equal f and then the integral from a to b, and then just dx, right? So then if we integrate this, it'll be, sorry, right? And then I have no space. So then that's also equal to that. So, and then b minus a, what's that distance? So, boom, it equals each other. Yeah. So, that's just like a little thing. So that's just like a little like background, basically, of what we will be working with. And usually there's like 3 different problems, or at least what we're working with for this class, for Calc 2. There's going to be spring problems, gravitational problems, and then like fluid problems, which is working with pumping like water and stuff like that. So this first example is showing a spring problem, as you can see, spring, right? So yeah, I'll read it out. A spring has a natural length of 20 centimeters. Okay, a 25 Newton force is required to keep it stretched to a length of 30 centimeters. Then how much work is required to stretch it from 20 centimeters to 25 centimeters? For this problem, F equals negative kx. This is another physics equation. Here, I'll put it in red. This is Hooke's law. So you kind of just need to understand how it works. You don't need to know the name, but it's just good to know, I guess, for the future. Hence, 1 Newton is defined to be 1 kilogram times meter per second squared. I'm sorry, and this is important because 1 Newton is in meters, but we have it in centimeters. So let me change my color. That's so dark. That's better. See, so make sure you pay attention to your minutes. So all distance needs to be converted. But sometimes they don't tell you. I think most times they don't tell you. They won't tell you, so you have to remember. Okay. Well, let's see. So what's important? So other than that, it's a spring. So natural length of 20 centimeters, right? And then 25 newtons force is required to keep it stretched. So that's telling us that if we want to draw it out, this is our spring, right? And it has a natural length of 20 centimeters. So the whole thing is 28 centimeters, okay? And an additional 25 newton force is required to keep it to 30 centimeters. So here are 30 centimeters, right? So this is just saying, this is our spring, and it's taking 25 newtons to stretch it out. So our spring would be from here to here, right? That's what it's saying. Okay, so it's being stretched out to 30 centimeters. Oopsies, wrong button. Another 10 centimeters, yeah. And then we call this x, I guess. Okay, and then it's saying then how much work is required to stretch it from 20 centimeters to 25. So it's saying that this is 25. Wow, that's beautiful. 25 newton to stretch it further. So now it's asking us if we have the same spring. Beautiful. Okay, 20 centimeters, and it wants to stretch another just 5. So to 25 centimeters, how much newtons would it take? Basically, is what this question is asking, right? So okay, so they give us this first one, right? So I'm gonna just write it out so you can see, but let's let x equal the distance, oopsies, of displacement. This is just fancy way of saying x is how much is stretched, right? Okay. And then okay, so right, work equals force times distance, right? And we're looking for how much work is required for this, right? So work equals force times distance. In this case, we can see that right here, that force equals negative kx. Keep in mind that this is k equals the spring constant, which basically means how much force it would take to move the spring. So in this case, it's negative. Well, no, in this case it's positive because we're stretching it out, right? So we're going to say that it's stretching this way is going to be the positive direction. So for us, f is just going to equal positive kx, right? But normally, sometimes it's negative because it's getting squished. If we're squishing the spring and we're making it smaller that way, the force would be negative. But since we're stretching it out, it's going to be positive. So just an FYI there, right? So then, because of that, work can also be rewritten as kx times our distance. And in our case, our distance will be I guess delta, right? Okay, so then if we want to rewrite it like this, we got work equals, and then now we got to figure out what our A and B is. Erase this. A is usually the displacements from rest, right? and then B is usually final displacement. But it honestly like depends on the question. Like, so like in this case right here, the spring, this is at rest, right? When the spring is like this, it's natural, it's x equals 0 right here when it's at rest. And we're trying to get it right here, which is 5 more centimeters, right? So that means x, x will equal 5 centimeters. But remember, this is in centimeters, this is in meters. So we can also rewrite this as 0.005 meters, okay? So, so our A and B here would be 0 from here, and then 0.05 here. Yeah? Ooh, wow. Sure, whatever. And then, so, you know, the function f in this case is kx and then dx, okay? And then, well, we can, now we have to figure out what k is, right? Because k equals a spring constant. I'm so sorry. I'm sorry, twin. I can't speak English. And so, like, how do we find k, right? Well, they gave us, you see, if a 25 Newton force is required to keep a stretch to a length of 30 centimeters, okay? They're telling us that, okay? So, right, I read in blue. So this one, okay, we're looking at this one, right? This is the first part of the problem. Force equals k times x, which is also, you see the x right here, the distance, okay? They're giving us this one right here, so we can figure out what k is, right? Because they're giving us the force, which is 25 newtons, 25 newtons right here, equals k times x, and the x right here, 30 centimeters to 20 centimeters, which is, see, x equals 0 or x equals 10 right here. Or since it's in meters, we can also write it as 0.1 meters. Okay, so I just have no space here, man. So we can also write, so it's 25 equals k times 0.1, right? And then you solve for k, and that's 25 equals k. So since k is a, I'll repeat it again, twin, a constant, it's going to be the same, and it's the same spring. The k for the first spring right here is going to be the same for the second spring right here, okay? So that means if we could plug in the k right in this problem right here, so work equals 0.050, so we have 250 x dx, right? And then take the integral of this, right? I'll move the 250 outside so you can see it better. I don't know if that's better, but right, like that. Take the integral, so we have 2.5 outside here, and then like that, and it's all going to be divided by 2, right? And then you do this part from 2. Wow, beautiful. 0.05 to 0, okay? And then I guess I'm going to put it over here, so 250 over 2. For this case, you can use, like, turn the decimal to a fraction, right? So it's easier, so this is also equal to 120, so 120 squared, right? Squared. Well, minus 0 squared, so that's just 0, right? So then you solve for this, and that's going to equal, let's see, that's 400, so that's going to be 5 over 16, okay? And that's your answer. And if this was physics, you would have to put the unit, which is joules, but since this is calc, I'm pretty sure you don't need the unit. But yeah, so yeah, that's your answer. That was your pause the video. Hopefully my handwriting's legible. It's a little bit cramped, but whatever. Okay, second question. Okay. Find the amount of work required to pull a dangling chain from length 5 meters and a mass density of 4 kilograms per meter up over the side of a tall building of height of at least 5 meters. So let's see. And we have, okay, building. It's saying height of at least 5 meters just to tell you that the chain is like less than the thing, so it's hanging and it's not touching the ground. So we have, okay, that's like our little guy, and then they're pulling this chain, okay? That's our beautiful, I should make it longer actually. So this is our building, this is our chain, okay? So we know that the chain is 5 meters, okay? So this is like the thing, and then this is the beginning, okay? In this case, I'm gonna say let y equal distance from top, because we're dealing with vertical stuff. Like this was horizontal, so I just use x for this time. Since it's vertical, I'm just gonna use y. You can use whatever you want. Doesn't matter. Wow, from. I'm so smart. I'm so smart, twin. From the top. Okay. So this case, y equals 0 from the top, and then this is the bottom, so y equals 5. Okay, so that's what they're telling us from right here. Okay. Mass density of 4 kilometers. Nope, 4 kilograms per meter, and then we check. Okay, they're in the same unit, so that's great. Perfect, actually. Right. So, okay, so what do we do? When we're working with equations like these, whoa, we're gonna look at the chain in like slices, right? Remember when we did the other integral stuff, and you looked at the washer method or the disk method, you looked at each like the graph in like slices. We're gonna do the same for here. So we're gonna look. So basically, we're gonna find the work of one small little slice, right? And then just add it all up for the whole chain, right? So in this case, let's say we're just going to take this little slice right here, right? And then this is going to equal, like since up and down is going to equal just like y, right? Wherever it is in the position is y. This our little slice is going to be just delta y. Yeah, right? So does that make sense? Like whatever this is minus that is going to equal that, yeah. It's going to equal the length of whatever slice we do. So so we have work. Okay, so let me do the work of our tiny little slice. Okay, equals force times distance, right? So what's the force in this case? Remember, they don't give us a force, so you gotta use that noggin of yours to think. In this case, they gave us the force. And since we're working with springs, the force is always gonna be negative kx. In this case, what force are we working with? I'm gonna give you 30 seconds. 3, 2, 1. We're working with gravity. So in case we've never taken a physics class ever, gravity equals mg, which is m is the mass, g is the gravitational constant, which is you don't need to know for this class, but it's like usually 9.8. But basically, what you need to know that this is a constant, and then this is a constant, right? So m g is our f, and then d. Okay, right? So we gotta break it down even more, right? So we're looking at m, right? Do we have an m? No, we don't. But what's m in this case? Like, how do we find m, right? M is also density times length, right? And density is the thing for that is rho. Ooh, that's beautiful. Rho times length. And is as we said over here, the length of whatever a slice is going to be delta y. Yeah. I don't know if I explained that correctly. I kind of like it's delta y because let's say this is like y2 minus y1, right? Goes our slice that we take. So like say this is y2, and we're looking at like I don't know, like whatever the thing is, like this is y1. The answer whatever is how thick we're, you know. So like this minus that is gonna equal whatever our thing is, or like if we're looking at this slice down here, y1 right here. If we're looking at this right here, right? And we minus this, like all of this minus all of this, we get the remaining length, right? I'm so sorry if that wasn't clear. Okay, you guys can't really ask questions, so I just whatever. So mass equals rogue. That's beautiful. Oh my god, rogue times our length, and then we still have g, and then times. Well, we can replace d in this case. And what's the distance, right? Well, we defined it up here. Let y equals the distance, right? So we can replace d with y here. Okay, and then if we're just like sake, you can just write it out. So we write it like this. So now we have rogue times g times y times delta y, right? So now this is going to equal our work of tiny, and then we can put it in the interval, right? We put it in the interval. So then, okay, let's do work equals, I got our thing. So what's A and what's B, right? So A is our starting one, which is 0. B is our ending, right? So it's 5. And they're all in meters, so you don't have to worry about that. So rogue times g times y, and then delta y is also dy, right? So look at that. So what can we like replace here? So or what can we take out? Is probably the better question. It's like we know that g is a constant, right? So we could take that out, okay? And then can we replace rogue? Well, that's density, right? So and they give us the mass density right here. So this is going to equal to 4. So we can also take that out. And then y and delta y we will keep, right? Because that's what we're trying to. So we got 4 g and then integral 5 0 y dy, right? That's x. Oopsies. So we take the integral of this, 5g, and then we got y squared, and then divided 2 from the y over 2, because it's like that, right? We take the integral. Well, I'm just going to put it on the outside, so it's easier to deal with, and then 5 0. So now we've got 5g over 2, and then minus 0, and then 4g. I guess we can simplify this, so that's just like 2g. Oh. 2g, and then times 5 times 5 is 25, right? And then this is equal to 50g. And that's your answer. Boom, we did it. Perfect, right? So, can't really, it's not a good view, but here's the whole thing. Yep. Okay, the next question, example 3, is like this one, but a little bit different. So, a heavy rate, what did I just say? A heavy rope, 40 meters long, has a mass density of 2 kilograms per meter and hangs over the edge of a 120 meter tall building. How much work is required to pull these, to pull 3/4 of the rope to the top? Okay, so important information, right? So the rope is 40 meters long and has a mass density of 2 kilograms per meter, right? This is not important. This is just telling us that the building is longer than the rope. Okay, so we don't ignore that. And then how much work is required to pull 3/4 of the rope. So that's super important. So I'll draw the little picture. Remember, look at these questions, you're like, ah, fuck, not another word problem, right? Just goddamn it, right? But just remember to draw your little picture beforehand, and it makes it like easier to work with. So in this case, it's gonna be, ooh, beautiful. Okay, so that's our building. This is our little guy, and he's pulling a rope. Okay, but we're only pulling 3/4 of the rope, so like that's like half-ish. So we're pulling 1, 2, 3. So we're pulling this much of the rope, okay, and then this is gonna stay like hanging off the edge. So basically, what that means is, I'll just draw the picture. That it's a curvy, it's a dusty building. It's okay. By the end of the pulling, there's gonna be 30 meters worth of rope up here, and then 10 meters worth of rope still hanging off the edge is what this means, right? Because we're only trying to figure out 3/4 of the rope. Okay, so let's see. So let's label everything. Okay, so we got again, let y equal distance from top. Distance from top. Oh, you get the you get the idea. So up here, y equals 0, and then since we're only looking for 3/4, right? Y is gonna equal to 30, and then the final is y equals 40. And just in case you're wondering where I got the 30 from, 3/4, right, times the total, which is 40. Because that's 10, so that's 30. Yep. Okay. So now we're also gonna label whatever the y position here is gonna be y. So whatever the distance is up here, like as we label, okay, is y. And then again, like this problem, we're gonna be looking at a single slice, right? So a slice here, and it's gonna be delta y. Okay. And then an important part that makes this equation different from this equation is that since we have stuff left over, we can't just like forget about it. We can't just like calculate just like 3/4 of it and just ignore this part, because we're still pulling this up, right? We're still pulling this leftover tin rope. We're just not bringing it all the way up, right? So now we have to split the problem into two parts. So we're gonna split it into the top part, which is all the way down here, and then the bottom part. Bottom, which is this remaining last 10 years, right? So okay, we'll start with the top. So okay, so we know that work equals well, work of one tiny slice, right? One tiny equals force times distance, right? And like this other problem, what is force? It's going to be gravity, right? So gravity is also mg times d. Okay, and like the other problem, how do we find the mass? Well, mass is also mass density times the length of our slice, right? And in this case, mass density, we're going to use rho to represent that, and then the length we're going to use delta y, right? And then d, we can also replace that with y, right? Because we defined it up there. Okay, yeah, don't forget the g. I almost forgot got it. Okay, so now what? Okay, I'll just write it out a little bit cleaner so you can see it. I don't know if that's cleaner, but it's easier to look like when you write it out like this, because you're pulling the constants up front and then the rest in the back for when we take the integral. So it's just like easier to look at in my opinion. But it's like whatever you want to do. So the work of the top, right? Take the integral. So what's our a and what's our b, right? Well, our a is always going to be 0. Well, in this case, it's going to be 0 because that's the top. And then since we're only doing 3/4, y is going to equal 30, right? And then rho times g times y times delta y, which also d, right? So now we can plug in our constants, right? We know that g, well, g is a constant, right? So we just take out g, and then we know rho, they told us, so we can also take that, and it's a 2. So rewrite this, 2g, and then integral y dy, right? And then you take the integral of this, right? So that's y squared divided by 2, and I'm just going to bring the 2 over here, right? I don't know if I explained that, that when you integrate this, it's 2, I mean, 1 to 6 power divided by 2 dx, not dx, sorry, just this, right? And I just brought the 2 out here, so it's easier to do the bounds. I don't know if I said that. So yeah, I just totally messed up right there. Sorry, twin. Forgive me, twin. Okay, so we do that. So now we have, wait, I shouldn't use so much space. I have to do the bottom too. 2g over 2, which is just g, sorry. And then y squared, which is just 30 squared. So then do that. So then 30 times 30 is going to be equal to 900g. So this is the work for the top part, remember? So this is only half of the problem, okay? So now we got to do the bottom, right? So bottom. Whoa, why is it red? I guess we do it in blue. Bottom. Do it a different color. Yep. Let's put bot. Okay, W bot. Force times distance, right? Like the one up here. So force, what is force? Gravity. And gravity is mg d. and do some mass too for rogue times length. And well, in this case, we know we could just use the full length, right? Because the reason why we use like piece by piece is because here, this piece right here is going to be moving up this distance, right? But the piece down here is going to be moving up this distance, right? Moving up this amount of distance, right? So the work on these two pieces are different. So that's why we use delta y, because it's going to be different. But in this case, since the whole thing is going to stop right here, it's only moving, like since from right here to up here, all of it is moving 30 up, right? Which means the length, in this case, it's going to be moving like as a unit, right? So because we don't have to look at each individual piece since it's moving all the same. So in this case, length would just be 10, okay? So I'll still write L right here for length, and then the G, and then distance in this case, as I just said, it's all moving 30 meters up, right? So, but I'm just gonna write D so we don't get confused. Right. So now we can substitute in. So rogue, we know, or the density is 2 times the length, which is 10, times gravity times the distance, which is 30. And then you multiply all that, so that's 300, 600. Yep. And G, and then you, that's since bottom, that's top, and you, W total is going to equal 900G plus 600G, which is going to equal 150G, and that's going to be our answer for this. Okay. So I can't really get all of it in one, but here is the first part, and then here's the second part. Yep. I hope that makes sense. For the water break. All right, next question. Okay. Find the amount of work required to pump all of the water over the top of a half-full cubic tank of side length 4 meters. Assume the density of water is P. Okay, so what the fuck, alright? Okay, so honestly, the pumping questions is not that different from rope questions. The main difference is when we're dealing with rope, it's like linear, right? It's a straight line. So that means that that the mass of one is just going to equal the density times whatever the length is. But for these, I guess, pumping questions, it's like you see this one's cubic tank, so I'll try to draw it to the best of my ability. Ooh, do not flame me, okay? I'm trying so hard. Just look like that. Okay, yeah, that's not too bad. So this is what our tank looks like, right? Right, so it's 3D. So since it's 3D, our mass is going to equal the density times the volume, right? Of like a slice, because we're still looking at slices, okay? We can read the question. So find the amount of work required to pump all the water over the top of a half-full cubic tank, okay? That's important. Side length 4 meters, so let's just say like each of the sides are 4 meters, whatever, right? And that's going to be half full, so half full. So this is our tank. It's like kind of half-ish. So like all of this water, okay? And for all these like questions, we're looking at like one slice, okay? To be able to like do it, right? Because remember, like this question, the water, it's getting pumped out, right? So the water right here getting pumped out, it's gonna move less distance than the water down here, right? It's gonna take more work to pump out the water at the bottom of the tank than the water at the top of the water line, right? So that's why we're doing it by slice. Whoa, my cube. Okay, let me just erase that. So this is gonna be the slice we're looking at. Okay, and then this is, I'm gonna take that. Perfect. That's kind of hard to see. It's okay. Okay, so some more labeling. So the top of the box, or the top of the tank, just like this, y equals distance from top, right? And then y distance from top. So that means the top of the tank is gonna y equals 0. The bottom of the tank, as it says, side length of 4, so the bottom is gonna equal 4, and it's halfway, so the halfway mark is gonna be equal to 2, right? And then similar to this question, one slice of like the water is gonna be delta y. That kind of doesn't look like delta y, and then whatever, like going up the bottom, it's y, right? Like distance. So okay, so now we're gonna do the thing. So we got the work of a slice is gonna equal. It's always gonna equal 4 times distance, right? Right, gang? Sorry, twin. I didn't mean to dead name you. I'm sorry. So force of distance, and then we're pumping water out. So what's the force we're using, or what's the force working against us? Gravity again. So force is equal to mg times d. And then remember what I said here, mass is equal to rogue, or density times the volume of a slice. Slice times g, and then d is y, right? So you can also rewrite this as rogue g y and then delta v, and then it's just like for memorization, because for the rope like stuff like this, your like delta work is always going to look like this equation right here. It's always going to be, for the most part, rogue times g times y times delta y, right? So this one right here, so it's easy to remember. It's going to be rogue y, rogue g y and then delta v. So the top one right here is when you're doing like these heavy rope kind of equations, and then this bottom one right here is when you gotta like pump liquid out. It's just like a little thing, so you can write it like that. It's just like to help you remember. And so now we're looking at this and we're like, okay, so now we gotta find the volume, right? Because we can't just integrate it, right? Because y and then what dv, that's different, right? So we can't do that. So we have to solve for delta volume right here. So slice. So how do we find the volume of one slice, right? Well, spoiler alert, it's gonna be the area of one cross section times delta y, so whatever the length is. So this case, the cross section is like this side times this side, like, you know, it's like this the square right here, right? So since one side is 4, we can do 4 times 4, which is 16. So the area of one slice is going to be 16 times delta y. Okay, so then we could plug that into this. So density times gravity times y times 16 delta y, and now we can integrate it. So I'll write it down here. Work equals integral. Okay, so now what's a and what's b? Well, I'll give you something to think. Okay, this is our tank, right? So if we want the water, which is at the halfway point, to get pumped out through the top, right? Where's the beginning at rest, and where's the like how much, right? Okay, are you thinking about it? If you answered A is 2 and then B is 4, you would be correct. Because right, the water line starts there, right? And it's because it's not a full tank. Yeah. Okay, great. I'm sure you knew that one. Okay. I'm sure you got that correct. So we got rogue. Man, my rogues are just getting like uglier and uglier as we go on. Okay, and then g times y times 16 times delta y. So now we can take our constants out, right? So you know, density is they don't give us density, but density is a constant, right? Gravity is a constant, so we take that out, and then we leave y, and then we can take 16 out too, because that is a constant. So we can rewrite it. Y equals 16. Oopsies, what is that? Density. Oh my god, it's so ugly. Wait, density times gravity, and then y. Oh, sorry, this is dy. It's dy. So when you integrate dy, it's y over 2, and then divided by 2, right? And then you integrate that from 4 to 2. So this is going to equal 8 times density times gravity, and then all that times 4 squared minus 2 squared, right? Which is going to be 16 minus 4. 16 minus 4, that's 12. Then 12 times A is going to equal 92. G. Oh, I'll be back. Oh, my bad. Rogue is P in this case. I've been calling it rogue. But it doesn't matter. I just used the wrong notation. So keep that in mind, I guess. It's P here for water. So yeah, it's P. Sorry, PG. PG. Okay. So that's our answer. Yippee! Here you go. You look at it for a second. Okay. Okay, final question, I think. Yeah. Oh, Jesus, I hate physics. Okay. Find the amount of work required to pump all the fluid, density P, out of a conical tank. Jesus, pointing upwards, height 4, and radius 2 if it's filled to a height of 2 initially. Okay. So after you have a little breakdown of like, fuck, it's physics, you know, when you see this on test, you draw it. You lock in and you draw it. So, conical tank, right? So it's a cone pointing upwards, so it's gonna look like this. Ooh, don't mind my amazing drawing skills, twin. Right, and it's like that. Okay. And then this is like the height thing, right? So it's like that. It's because it's a triangle, it's a cone. So radius is going to be 2. Here, I'll write it in green. Why not? Green. So that's our radius. Can you read that? That's 2. Right, the radius is 2. Sure. And then height is 4. So this is 4. Okay, so let y equals this to top. Right, so this is our top, so y equals 0, 0. The whole thing is 4, so down here it's going to be y equals 4, and it's filled with water to a height of 2 initially, so that's So it's like here. Ooh, whoa, what is that, water? Here, I'll move the 4. Kind of like in the way. Oh, my cone. Okay. This is water, okay. Oh, this is water, okay. So the whole thing, 4. Okay. And this is height of 2, so this is y equals 2. Okay, so let's do the work of, and again, we're looking at one little tiny slice, right? Same reasoning for this, right? The water down here is going to take more work to get out than the water up here, so we got to look at it from slice by slice. So round color. Work out tiny equals force times distance. Yup, when you know it. And then what's force? Again, well, it's like this case, but a different shape. So gravity is going to be working against us, so it's going to be mg times d. What's m in this case? Density times the volume of a slice. So density times volume of a slice. Times g times d, which in this case, as we have defined it, equals to y. So we can just write right here. And if you want to rewrite it a little bit, so it looks, so you can compare it to see if you got it right. D, y, and then delta b. Right. So now we gotta find out what delta b is, right? For one slice. Oh, that's beautiful. Okay, I'll do it in different colors. Right here. Whoa. Okay. B slice. So like the other one, we gotta find the area of a slice, or there was a cross section, right, times the length of one, which is just delta y, right? So what's the area of one cross section? So in this case, it's a square, right, because it's a cube, so it's just like 4 times 4. But since it's a cone, we gotta think a little more, right? So since the cross section, like what shape is that, right? It's a circle. So in this case, the area is gonna be pi r squared times delta y, right? But we have to figure out what r is, right? And they say r is equals 2, right? But we can't use that. Why? Is it why you ask? I think I heard why. It's because the triangle. Here, I'll draw it out. I'll draw the cone out. So this is our thing, right? This is our cone. This is our water line, right? And then this is like the middle, right? This because remember this is a triangle. Wow, that's not straight. This is our zesty middle triangle, okay? So it's saying that this r right here equals 2. I don't know if you can read that. But the triangle all the way like up and down here, right? This triangle is a different size from like a triangle from like the water line, right? Like if we were to draw triangles, like it's different, right? So this r right here is not going to be equal to, because as we see the cone is getting smaller and smaller, right? The r is getting smaller and smaller. So the r2 here is not going to equal to r2 here. So we can't use r equals 2 here. So we have to find out the ratio, right, of r as it's approaching the top. So how do we do that? We use a little thing called similar triangles. Sim trig. Okay. So that this thing is basically saying that if we have a triangle here, here I shouldn't write it so big. A triangle. If we have this triangle, and then we have a triangle inside of this triangle, the ratio of this to this. So the ratio of this r divided by whatever this r is going to be this. Is going to be here. I'll label this 1. Label this 2. Right. So that that's going to be the same ratio as this y right here. I'll use a different color. I'll use whatever this color is. No, I'll use blue. The y here, or I guess height, I should know. This h here, and the total h, right? Does that make sense? This is h1, this is h2. That's a b, it's not h. Does that make sense? So, because we're making the triangle smaller, right? So by making it smaller, the ratio is going to be the same. So if we use this logic, right, to this, well, r1, in this case, is going to be the triangle like up here, right? It's going to be the smaller triangle, so we got, it's going to equal to just r, and r2 down here, well, they told us it's going to be 2, right? And then height 1, which in this case, we're gonna just call it y, right? Like whatever this from this here, it's y, because it's like y equals distance from top, right? So that's how we labeled that. And then whatever height 2 is, right? What's the height of the whole thing? They tell us it's 4. So they give us this. So this is the same ratio. So if we try to solve for r, multiplied by 2, so now r equals y over 2, right? Right. So now we have our r. So I should write it down here. I'm gonna rewrite it here. Equals r equals y over 2. I'm gonna erase this. So now our thing is going to be y over 2 squared times delta y. Okay, so now this equation right here is going to be equal to the delta volume per slice. Okay, so now we can plug it back in here. So we have density times gravity times y times the volume, right? So we've got pi y over 2 squared, so we need y squared over 4, and then the delta y. And now that we have that, we can integrate it. So, alright, or total equals the interval of, now we have to find out what b and a is. A is going to be the bottom, right? So a here to b here. So a in this case is, I'm sorry, the opposite. This is a right here, this b right here, because a has to be less than, right? So it's going to be like that. And then p, or density times gravity times y times this thing, 4, right? Or this is dy. Okay, so now we can take our constant down. So density is a constant, gravity is a constant. We keep y, and well, pi, and then divided by 4 is constant, right? So we take that out too. And since it's like divided by 4, so like the whole thing can be rewritten as like everything divided by 4. So like in case you're confused, I just go. It's all over 4, right? So then you could just take the 4 out. In case you forgot, in case you forgot your integrating lessons, which you should probably brush up on those. So now we take this out. So we have pi. I guess we have density times gravity times pi, and then we take out the 4. Great. Oopsies, that's not a interval 4 2. Now we're left with y times y over 2. So this is y3 times dy. Right. Take the interval of this. P times gravity times pi 4, and then well, this is going to be y4 divided by 4, right? So we bring the divided by 4 out here, and then you bring the balance through. So density times this divided by 16, and then now it's 4 to the 4th power minus 2 to the 4th power. So this is, let's see, ooh, gotta use my brain. I think, this is 16, right? So this is like, wait, no, this is 256. This is 256, and then minusing that is 240. So g pi, I guess times 240 divided by 16 is going to equal 15 p g pi, and then this is the answer. Yippee! We did it. Yep. Here's the work. I tried to explain it to the best of my ability, twin. So sorry if I confuse you, twin. Let me know if you have any questions, and good luck. Bye bye.